Hey math fans, in the last video we started talking about infinite families of events, and we said that if we had an infinite family of events such that they're all nested inside of each other, okay, so A1 is entirely contained in A2, entirely contained in A3, and so on and so forth, then we have that the probability of this infinite union of all the events is simply the limit as n approaches infinity of the probability of a sub n, which is easily seen by this diagram right here. I can keep extending this out, and the more I extend it out, the easier it is to see that the union of all the events is everything. Okay, so you can attain that just by taking the limit if you have an expression for the probability of a sub n. Okay, so we're going to prove a couple of consequences of this and then go straight for the first Borel-Cantelli Lemma. Let's get started with the corollary to this. Corollary. So the corollary says, okay, what if you don't have a sub 1 contained in a sub 2? What if it's contained in a sub 2? So that means that for a sub 1 contained in a sub 2, which is contained in a sub 3, and so on and so forth, can we do the same thing? Kind of, right? So the result we're going to get right now is that the probability not of the union, but of the infinite intersection of the events a sub k. And it turns out that's the only thing that changes. It's still going to equal the limit as n approaches infinity of p sub a sub n. Okay. All right, let's prove this. And a corollary, by the way, just to remind you, is like an immediate consequence of a theorem. It doesn't have to be that immediate, but it should be based on the theorem you just proved. All right, so proof. Okay, so this is going to rely on a fact that I asked you to verify in a previous video, but that fact is if x and y are sets, and x is contained in y, that implies that actually the complement of y is contained in the complement of x. And you can just draw a Venn diagram. Take a minute, pause the video, draw a couple of Venn diagrams, prove this to yourself before we start. Okay, so here's how the proof is going to look. So if a sub 1 is really contained in a sub 2, and so on and so forth, then we have that actually the complements go this way. Okay, so from this situation, we can immediately use theorem 2.3 in the following way. To say that probability of this infinite intersection is equal to what? Well, recall again that the probability of some event x is equal to 1 minus the probability of its complement. Okay, so I'm going to use that fact now. And we're going to say simply, because I want this to turn into the complement of this. I'll show you why in just a minute. So this is going to equal simply 1 minus the probability of the complement of this event. So I'm going to just write it down exactly as before, but then I'm going to put the little complement bar over it. And this is by the definition of the complement. Okay, so now I have the complement of an infinite intersection. So that should scream De Morgan's laws to you. So by De Morgan's, this is simply the probability of the union of the complements. Okay, so I flipped the intersection to a union, but now the complement goes over each a sub k. Okay, and that's by De Morgan's. Okay. But then we have theorem 2.3 that we can just use on this guy because all the a sub k complements follow this little pattern. Okay, so this is going to equal 1 minus the limit as n approaches infinity of the probability of a sub n complement. Okay, so this is, again, this is using theorem 2.3. This is where that comes in front. And then by a property of limits, I can really just take this limit operator and just pull it out, right? Because the limit of a difference is the difference of the limits, and the limit of a constant is just that constant. So this is the same expression as if the limit was just out in front. 1 minus the probability of a sub n bar. Okay, but then the reason that I wanted to do that is this, by definition, this is 1 minus the probability of the complement, which is just the event itself. Done. Okay. Now we have one more theorem before the Borel-Cantelli Lemma. We'll go ahead and call it theorem 2.4. And it says the following. For arbitrary events A1, A2, and so on, we have that the probability of this infinite union, the one that we've spent a lot of time talking about, is less than or equal to the infinite sum of the individual probability of a sub k's. Now think about that for a second. This should scream a little awkward to you because we had a definition right here, the star definition. Probability of the infinite union was just the sum of the probabilities. Well, yes, that is true for mutually exclusive events. But as we saw earlier, if even two events aren't mutually exclusive because there's some overlap, then that probability of A, assuming maybe this is A1 and A2, is equal to probability of A1 plus probability of A2, or in other words, the sum minus the probability of this intersection. Okay, so we're already kind of seeing why the union might be smaller than just summing everything together. Okay. So the proof is going to rely on the disjointification of the family B sub k, which we talked about in the previous lecture, so you might want to refresh your memory on that. Otherwise, it's pretty straightforward. So proof. We're just going to use the disjointification, the families B sub k, where k is in the natural numbers, in the following way. So the disjointification means that this family is actually all mutually exclusive, and the union of this is equal to the union of a sub k. Okay, so that means that the probability of this infinite union, that it's not necessarily mutually exclusive, this union is the same as this union. And that union is mutually exclusive, which means this is going to equal the sum from k equals 1 to infinity of the probability of the b sub k's. Now, this relies on the following principle. B sub k is a subset of a sub k. Right? Remember how we define this, right? B1 is equal to A1, B2 is equal to A2 minus A1. So right there, we have the fact that if this is A1, A2 is maybe all of this, but B2 is only a subset of that. Okay, so this holds for any B sub k. It's always going to be a subset of A sub k. Okay, so since that holds, the probability of this is less than the probability of that. That was one of the properties discussed in a previous lecture. And then if we have an infinite sum, you can just apply this an infinite number of times. And we get simply that this is less than or equal to the sum of the probability of the A sub k's. All right? Okay. So now we have our final result, theorem 2.5, which is only the first of the Borel-Cantelli lemmas. I'm only going to prove one of them. And maybe we can discuss an example. Okay, so this is the first Borel-Cantelli lemma. It's the first. Okay, and it says the following. Given events A sub 1, A sub 2, and so on, that occur with probabilities, which I'm going to define p, little p sub 1, little p sub 2, and so on. Okay, so i.e., what I'm saying is little p sub 1 is equal to big P, the probability of, okay, little p sub k is the probability of A sub k. It's just some shorthand that'll be helpful. Okay, so given all these events with all these different probabilities, let's suppose I just add up every single probability of these infinite events. So I'm going to consider the infinite sum from k equals 1 to infinity of all the little probabilities p sub k. And I'm going to tell you right now up front that this sum converges. So that means that this sum is less than infinity. Then it is certain that only finitely many events from this family occur. That's a pretty powerful statement. So convergence implies that you only have a finite number of events that could possibly occur. All right, let's prove this. Proof. First thing we're going to need to do is we're going to need to set up a couple of events. Okay, so we're going to go ahead and let B be the event that infinitely many events, A sub 1, A sub 2, and so on, infinitely many of those events occur. And we're going to go ahead and let B sub n be the event that at least one of the events, and this time we're going to start at A sub n plus 1, and so on. So at least one of those occurs. Okay? So then we have a couple of ideas here. Okay? So we have that this B sub n that I've defined is actually going to be the union of A sub k's, where k is bigger than or equal to n. So pause the video, think about that for a second. So B sub, just as a quick example, B sub 5 means at least one of A sub 5, A sub 6, and so on occurs. And that is going to be a union where k is bigger than or equal to 5 of, well, let's see. It's going to be a union of A sub 5 or something bigger than 5, A sub 6 or something bigger, A sub 7 or, and so on and so forth. So those actually do match up. Okay, and I'm going to call this 1. And we also have that the event B infinitely many events a sub 1, a sub 2, and so on occur, that is going to be the intersection of all n equals 1 to infinity, of all of the b sub n's. Okay. And I'm going to call this 2. So I'm going to pause the video, confirm it with a couple of examples before we move on, because we're just going to start using these in the proof. So if it doesn't make sense, stop. All right, so back to the proof. So we have that the event B, we can just kind of substitute this in for b sub n. And we get that b is equal to this intersection from n equals 1 to infinity of b sub n, which is really the union over k bigger than or equal to n of a sub k. Now, just by kind of looking at this, b sub 1 is the event that at least one of the events a sub 1, a sub 2, and so on occurs. So clearly, we have that b sub 1 is fully contained in b sub 2. Why? Because b sub 1 says that at least one of these occurs. B sub 2 means at least one of these occurs. So this clearly contains this, and so on and so forth. Okay, so this continues forever. Okay, and now if you're thinking, oh, maybe I can use the Corollary of Theorem 2.3, you'd absolutely be correct. So we have that the probability of B, which is the probability of this infinite intersection, which is really the intersection n equals 1 to infinity of the b sub n's, that is going to equal the limit as n approaches infinity of the probability of each b sub n. Okay. However, note that the events a sub 1, a sub 2, and so on are not necessarily mutually exclusive. In fact, you can just assume they aren't mutually exclusive. So, by what I've designated number 1, we have that this probability, the probability of b sub n, is less than or equal to, well, let me do it like this. So the probability of b sub n, what is b sub n? B sub n was given here. So I'm just going to write that. It's the probability of this union, where k is bigger than or equal to n of the a sub k's. And this is actually not by 1. This is actually by, I think it was theorem 2.4. Okay, and I'll explain why in just a minute. So the probability of b sub n is equal to the probability of this. I just plugged it in. Nothing complicated about that. But then this union right here is going to be less than or equal to the sum. Okay, so that's the same thing as this, but we have to put that less than or equal to probability of each a sub k. Okay, so this is where we used theorem 2.4. All right, let me just remind you really quickly what theorem 2.4 said. Said that any arbitrary union of events a sub k is less than or equal to this infinite sum. So just summing all of them will always be greater than taking the probability of the union. Okay, so finally, we have that the probability of B is equal to, from up here, it's the limit as n approaches infinity of the probability of B sub n. So that is the limit as n approaches infinity, the probability of B sub n. Okay, so the probability of B is equal to the limit as n approaches infinity of the probability of B sub n. Okay, so that's by star. And then by double star, we have that the probability of B sub n is less than or equal to this sum right here. So that means the limit as n approaches infinity of this must be less than or equal to the limit as n approaches infinity of the sum, k bigger than or equal to n, of the probability of a sub k. Now remember this, we went ahead and defined that as little p sub k. Okay, so we have that the probability of B is less than or equal, I'm just copying this. The probability of B is less than or equal to the limit as n approaches infinity of this sum from k is bigger than or equal to n of p sub k. Okay, but this can be considered as a partial sum, right? Because we're only summing from p sub k, which is bigger than or equal to n, to infinity. And I will tell you that this partial sum has to decrease, and it has to approach 0 because of the hypothesis that the sum of all of them was finite. And by definition of finite sums, a finite sum is such that the limit of the partial sums goes to 0. So the probability of B is equal to 0, which means that that's not going to happen. Well, what was the event B in the first place? B was that infinitely many events occur. Meaning infinitely many events cannot occur. And thus we've proved the lemma. Now, let me just give you an example of where this might be useful. All right, so this is just like a little example. Let's suppose that you're flipping a weighted coin. Okay, so it's not exactly probability 1/2 heads and tails, but suppose, I don't know, suppose probability of flipping a weighted coin was given by, we'll say a sub k is the probability of flipping heads. Heads on a weighted coin, and we'll say that probability is equal to, we'll say 1 over k squared. Okay. Now note that if I'm summing over all possible values of k, so the first trial, the probability might be 1. The second trial, the probability is going to be 1/4. The third trial is going to be 1/9, and so on and so forth. Note that the infinite sum from k equals 1 to infinity of all the probability of a sub k's is equal to the infinite sum from k equals 1 to infinity of 1 over k squared. Well, that actually does exist. It's finite. I think it's pi squared over 6, which is less than infinity. So by the Borel-Cantelli Lemma, theorem 2.5, you can only flip heads a finite number of times. Or expressed a different way, there exists some integer, some natural number, such that all events after that are tails. So that's the Borel-Cantelli Lemma. This was chapter 2. I hope this was helpful. In the next video, I'll be working out some of the exercises for you. See you then.